Comprehensive overview of spectrum. Spectrum allocation refers to the process of assigning specific portions of the electromagnetic spectrum to various services or users to ensure the efficient use of this limited and vital resource. The electromagnetic spectrum is a continuous range of electromagnetic waves, radio waves, microwaves, etc., that can be harnessed for communication, broadcasting, scientific research, and other applications. Since the spectrum is finite and demand for wireless communication continues to grow, managing its allocation becomes increasingly important. Key concepts in spectrum allocation 1. The electromagnetic spectrum. The electromagnetic spectrum is the range of all frequencies of electromagnetic radiation. It is typically divided into several bands, each with distinct properties and uses. The most relevant part for spectrum allocation is the radio frequency RF spectrum, which is further subdivided into different frequency bands. Radio waves, 30 Hz to 300 GHz, are used for various types of wireless communication. The spectrum is divided into different frequency bands, each allocated for specific uses. The spectrum is categorized into low, mid, and high frequency ranges, and each range has unique characteristics. 2. Frequency bands and their uses. The electromagnetic spectrum is divided into numerous frequency bands, and each band is typically allocated for specific uses, depending on its propagation characteristics. Here's a breakdown. Extremely low frequency, ELF, 3 Hz to 30 Hz, used for very long-range communications, such as submarine communication. Very low frequency, VLF, 30 Hz to 300 Hz, used for long-range radio communication, maritime communications, and some scientific uses. Low frequency, LF, 300 Hz to 3 kHz, used for AM radio broadcasting, maritime communication, and time signals. Medium frequency, MF, 3 kHz to 30 kHz. AM radio, AM broadcast radio, operates between 530 kHz and 1,700 kHz, and maritime communications. High frequency, HF, 30 kHz to 300 kHz, used for long-range aviation communications, shortwave radio broadcasting, and some satellite communication. Very high frequency, VHF, 30 MHz to 300 MHz, used for FM radio, television broadcasts, and line-of-sight communications. Ultra-high frequency, UHF, 300 MHz to 3 GHz, used for television broadcasts, mobile phones like 4G, GPS, and Wi-Fi. Super high frequency, SHF, 3 GHz to 30 GHz, used for satellite communication, radar, and some wireless broadband applications. 5G, Wi-Fi 6. Extremely high frequency, EHF, 30 GHz to 300 GHz, used for advanced communication systems, scientific applications, and military radar. Terahertz, THz, 0.3 THz to 3 THz, still emerging as a frequency band for ultra-fast wireless communications and imaging technologies. Key processes in spectrum allocation 1. Regulation and governance. The allocation and management of the spectrum are typically governed by both national regulatory authorities and international bodies to ensure efficient, interference-free operation across borders. The process is highly regulated to minimize interference between services and users. National authorities. In most countries, spectrum management is handled by government agencies such as the Federal Communications Commission, FCC, in the United States, the Ofcom in the United Kingdom, or Spectrum Management Directorate, SMD, in India. These organizations are responsible for assigning spectrum to different services, regulating its use, and enforcing the rules. International coordination. Since radio signals can travel beyond national borders, spectrum allocation is coordinated internationally to avoid interference. The International Telecommunication Union, ITU, a specialized agency of the United Nations, plays a key role in global spectrum regulation, It develops international treaties, such as the radio regulations, which establish global standards for spectrum usage. 2. Licensing and spectrum auctions. Spectrum is a finite resource, and allocating it efficiently requires careful planning. Traditionally, governments allocate spectrum through a system of licensing, where operators are granted rights to use certain frequencies for a specific period. This can be done through direct allocation. Governments allocate spectrum to specific users or services, typically for long-term use. This approach is common in the case of public services, e.g., broadcasting or military use. Auctions. More commonly in recent years, spectrum rights are auctioned to the highest bidder. Governments hold spectrum auctions, where companies, e.g., telecom operators, bid for the right to use specific frequency bands for wireless communications. This approach is prevalent in the allocation of spectrum for mobile networks, e.g., fourth generation, fifth generation, and broadband. The auction model is advantageous as it creates a market-based approach to spectrum allocation, ensuring that spectrum is assigned to those who value it the most and are willing to invest in its use. 3. Spectrum sharing. As demand for spectrum grows, there is increasing interest in spectrum sharing as a way to maximize efficiency. Spectrum sharing involves multiple users or technologies using the same frequency band without causing harmful interference. There are different models of spectrum sharing. Static spectrum sharing. Different users are assigned specific portions of a frequency band. Dynamic spectrum sharing, DSS. Technologies such as 5G can dynamically share spectrum with other services, e.g., Wi-Fi, based on demand, location, or time of day. Cognitive radio and software-defined radio, SDR. These technologies allow more flexible and efficient spectrum use by dynamically adjusting transmission parameters based on the current conditions of the spectrum. Cognitive radio can detect unused portions of the spectrum, called white spaces, and use them without interfering with other services. Fourth, impact of emerging technologies. With the rapid development of new wireless technologies and services, like 5G, 6G, IoT, and Wi-Fi 6, spectrum allocation must adapt to meet the needs of these technologies. Some trends include higher frequency bands. Advanced services like 5G and Wi-Fi 6 require higher frequency bands, e.g., millimeter wave spectrum, which provide high bandwidth but have shorter range and less penetration. These require dense deployment of infrastructure, e.g., small cells. Unlicensed spectrum. Parts of the spectrum, e.g., Wi-Fi, Bluetooth, are made available for unlicensed use, meaning any device can use these bands without needing a specific license. This fosters innovation, but also requires careful management to prevent interference between devices. Shared spectrum models. Technologies like Citizens Broadband Radio Service, CBRS, in the U.S. allow for shared spectrum between commercial users and government entities, like the military, improving efficiency and making more spectrum available for use. 5. Global harmonization of spectrum. Because spectrum is a transnational resource, global coordination is essential to avoid interference between services operating in neighboring countries. The ITU coordinates the global use of the spectrum through the World Radio Communication Conference, WRC, which is held every 3 to 4 years. The WRC reviews the global allocation of frequency bands and establishes new regulations to accommodate emerging technologies, such as 5G, satellite communications, and the Internet of Things. Challenges in spectrum allocation 1. Interference. Ensuring that different services do not interfere with each other is a major challenge in spectrum allocation. Interference can cause poor quality of service, dropped connections, and even security risks. 2. Demand for spectrum. With the growth of wireless data demand, particularly from mobile devices, IoT, and emerging technologies like autonomous vehicles, the demand for spectrum is increasing exponentially. This creates pressure on existing allocations and drives the need for more efficient spectrum management. Third, technology evolution. As new technologies are developed, they may require new spectrum or cause interference with older technologies. Managing the transition from older technologies, e.g., 2G, 3G, to newer ones, e.g., 5G, 6G, without disrupting services is a complex process. 4. Equitable access. Ensuring that spectrum resources are allocated equitably, especially in developing countries, is important for bridging the digital divide. Fair access to spectrum for rural areas or underserved populations can enable economic growth and technological advancement. 5. Sustainability. As the number of wireless devices grows, there's a need to manage the energy efficiency of wireless systems and minimize environmental impacts, which could become a consideration in future spectrum allocation strategies. Conclusion. Spectrum allocation is a complex, dynamic process that plays a crucial role in the development of modern communication technologies. As demand for wireless communication increases, effective and efficient management of the spectrum is essential to ensure that technological innovations continue to thrive. The combination of regulation, technology evolution, market-based allocation methods, like auctions, and international cooperation ensures that spectrum resources are used optimally, minimizing interference and maximizing benefits for all users. Please remember to like, share, and subscribe for more updated and latest information generally on technology at Comfort Zone 11 Piece.